G'day all. For the physics senior curriculum course, all the rest of our labs are in the lab, or at least in years other than 2020 when we're all social distancing, and we're doing some video recordings of the labs, and you will be either approximating or simulating the labs at home or just using our data from the video labs. But most years what we're doing is doing all of the labs on campus except this one. This one is an online lab session that we'll do, and the plan basically is to use a simulation. Now, we don't actually own a photoelectric effect apparatus. There is such a thing. You can physically do the experiment, obviously. In fact, they were doing it in the late 1800s, and the photoelectric effect was one of those things that they didn't fully understand until Mr. Albert Einstein came along and explained it. It was one of the first big important papers that he did, was creating an explanation for the photoelectric effect in terms of quantization of charge and also quantization of energy in photons. So basically, Einstein's experiments on the photoelectric effect took us back to a photon model of light, which had been largely discarded after Huygens and after the Young's double slit experiment back in sort of Newton's time. But that's probably a bunch of content that I go to in the content videos. This is just about the lab. So what I'm going to do is use one of the PhET simulations. You're probably familiar with those already as a physics person. The PhET, the Physics Education Technology Project, I believe it's called, at the University of Colorado, produces some great simulations. There are other places that produce simulations as well. But the PhET ones are really well designed. They're simple. They just work. Although I've decided to do this on my Mac today. On Windows, they'll usually just work, although you have to make sure you have Java installed before you try and run them. If you download the jar file, the .jar file for the simulation or application that you want to use from PhET, and double-click it, sometimes Windows will say, would you like to open it with Java, or would you like to open it with like WinRAR or WinZip, an unzipping program? Don't do the latter. Open it with Java and it'll just open and run. And Windows is pretty painless. I decided to do it on Mac because it will show you the potential hassle on Mac. But I'm just going to search PhET and photoelectric because I know they have one, PhET, photoelectric effect. And it's that one. I'm going to download the jar file. Going to take a moment to download. I'm using Chrome as well. It'll look slightly different if you're using a different browser, but basically you'll know where your downloads go. Okay, it's asked me whether I want to keep it because it's scared of external files, because people can do awful nasty things in Java, but the nice folks at PhET don't do that. Now if I double click on it, I'm going to get an error message that says it can't be opened because it's from an unidentified developer. So Apple has basically said, we want you to buy everything from the Apple Store, so we're not going to open stuff from other developers. But and so it looks as though you're stuck, but you're actually not. So if you go to System Preferences, Apple menu, System Preferences, Security and Privacy, then it's actually showing down the bottom here, allow apps downloaded from blah, photoelectric.n jar was blocked, and there's an open anyway button. So just click the open anyway and it will open that now. Tell it to open it. So there's a few warnings, but it's actually relatively easy to get it to work on a Mac, and probably just as easy or easier to get it to work on Windows. You also need to install Java on your Mac, of course. I don't know if I mentioned that. Now, what's the photoelectric effect? Basically, if you shine light on a sample of some metals, after a while they will start to emit electrons from the surface. And there are certain rules about how the wavelength of the light, the intensity of the light, and then the energy of the emitted photoelectrons. So it's the photoelectron effect because photons cause metals to emit electrons. So what have we got down here? We've got a current of 0. There's no photoelectrons at the moment because the light's turned off. So if we turn on the intensity of the light, so we're actually starting with a light down in the UV, in this case, we have a sample of sodium. If you have a look over the side here, we've got a number of possible metals we can do, or if we want to check the student's understanding, there's an unknown metal that they can use the photoelectric effect to determine what metal it is from among these ones on the list. So sodium, zinc, copper, platinum and calcium. So we'll start with the sodium sample. We've got a number of settings here. Current versus, we can create graphs that will show as well as the actual apparatus. So the apparatus is like so. You've got a light beam which is going to shine on that sample of metal. So that grey layer there is our sample of metal. It's connected to electrodes. It's in a vacuum tube so that the molecules of the air don't get in the way of the electrons. It's connected and we've got an ammeter on it. And we've also got a battery so that we can put a voltage, either positive or negative, on the electrodes. And we'll see about that in a moment. So if we turn our light on, so I'm just going to slide up the intensity slider. You can see my light, and immediately that I turn the light on at all, you can see that there are photoelectrons being emitted. They're at a range of speeds. They are going to the other electrode, and you can see now our ammeter measuring the current shows that there is a current for a particular intensity of the light, and the increase in the intensity of the light increases the current. That makes sense because your photons are coming in, releasing your electrons, and more electrons flowing around the circuit means more current. Right, that makes sense. Now, let's just pull the intensity back to 0. We know that the UV is the high energy end of the spectrum, so let's go way up the other end of the spectrum, up into the blues, the greens, the yellows, the reds, the oranges, and right up to the infrared. Now, let's try the same experiment. If I turn my light on, and if I keep turning my light on, no matter how intense I make the radiation in the ultraviolet, you can see it doesn't really show up because ultraviolet's invisible to human eyes. Sorry, infrared is invisible. But I can make it as intense as I want. I won't get a current flowing because photons of that long wavelength, low energy, it's E equals hf or E equals h nu. The energy of a photon is Planck's constant, h times its frequency. So it will, long wavelength, low frequency energy has less energy, and in this case it doesn't have enough to emit electrons from the sodium. Let's see whether it will for any of the other metals. Are there metals for which an infrared photon will emit photoelectrons? Zinc, test it, lots of intensity, no. Copper, cranking it up with the IR, no photoelectrons. Platinum, no. So right up in the infrared here, we'll test our last metal for completeness. Calcium, the photons simply are not energetic enough to emit photoelectrons. So let's go down into the green. So 513 nanometers. We're on calcium still. Is that energetic enough photons to emit photoelectrons from calcium? No. We'll test the other metals. So I won't continue going through all of this. So I'll go to sodium with green light. Do we get any photoelectrons with sodium with green light? We don't. Oh yeah, we do. With very high intensity, we get a few. Actually, we should get some with lower intensity as well. So we're getting a few at low intensity. And that means we should get some at very low intensity. There might not be a lot, but even down at 4% intensity, we still are getting the odd, fairly rare photoelectron emitted from a sodium surface with a 513 nanometer light. Now let's go to, we'll stick with the sodium, we'll pull the intensity down, we will go to a more energetic form of light. So we'll go down to the indigo. So we should get more photoelectrons. We've got our intensity. Now, the other concept that we've got is stopping potential. So the stopping potential is actually a measure of how fast the electrons are going when they come out. So the electrons have energy by virtue of the fact that they have velocity, because they don't have much else. They don't really, they do have spin, but it's not a kind of spin that stores energy. They basically have energy because of their velocity. So you can see clearly that some of them are going faster than others, and we can apply a potential. So if I apply a positive to the right hand electrode, make it plus 1.4 volts, that's going to accelerate the electrons, because they're negatively charged electrons. They're starting from the left, they're being attracted to the right and repelled from the left. So that's going to speed it up. So what if we go the opposite way, if we put a negative voltage across? So you can see that it's starting to slow them already. And you'll find that most of them will be actually recaptured by the surface now. So that's at minus 1 volt. And you can see that most of them will be recaptured by the surface, because they don't have sufficient energy or sufficient speed to overcome that voltage. So if I make that negative voltage slightly smaller, you can see some of them, the fastest ones, get further. The stopping potential is defined as the voltage that will stop any current from flowing. And so far we're further than the stopping potential. The stopping potential is the threshold at which the current just stops flowing, but it's completely stopped flowing at the moment. So let's reduce that potential even a little bit more, down to 0.2 of a volt. And you can see some electrons are making it. There's a very tiny current now flowing, because the very fastest electrons are making it. So clearly minus 0.2 volts is not enough for the stopping potential. Minus 0.6 volts is too much. Minus 0.4 volts, yes, there's a very tiny, it's not a measurable current at that point. But you can see occasionally an electron gets there. It's fairly rare, but occasionally they'll get there. So these are the features of the photoelectric effect. And what I'm not doing here really is explaining, excuse me, what the features mean, except that different metals have different work functions. The work function is the amount of energy it takes to release an electron. Remember that in the body of a sample of metal, of pure metal, the valence electrons are delocalized. They're not hanging with a particular atom. They are in a sea floating around all of the nuclei. And to remove one of those electrons, you have to provide it with some energy. The stopping potential is the amount that it requires to just get it free with zero velocity. In other words, no more energy than it absolutely needs to get out of jail. If you provide more energy than the work function, then you'll give the electron some velocity. It will have some energy that it carries away as velocity. So the different metals have different work functions. That means that they will emit at different wavelengths of light, and then the energy of the remaining energy in the photons is what in the electrons from the photons. So the photon brings in a packet of energy. Some of it is used to overcome the work function. The rest is used to give velocity to the electron. And the stopping potential basically is a measure of the maximum amount of energy left over in the packet of energy from a photon after the work function is overcome. So obviously there's calculations you can do around that, and that's what you should do in your write-up of this lab. You should talk about the features of the photoelectric effect, the features of the photoelectric effect experiment, what is the meaning of intensity, wavelength or frequency of the light, work function and the stopping potential, and the calculations of same. So what does the experiment mean? Now you can play with this apparatus more. There are different graphs you can create. So if we take the stopping potential off, so I'm going to go back to 0 volts, then crank up the intensity and graph the current, what we should get as the intensity goes up is an increase in the photocurrent. And you can see that that's what we've got. As the intensity was increased, the photocurrent was increased. We can zoom that graph up a little bit to make it a bit easier to read. So there's this linear relationship between the intensity of the light and the photocurrent, and I think I need some more data points down the back. But there appears to be a drop-off point there as well, that if the intensity is too low, you won't get some. So have a play with that. There's electron energy versus light frequency that you can play with. You can reset the whole system and start again. You can show the photons coming out of the light or not, as you wish. It's interesting that they look physically bigger than the electrons, because they probably really shouldn't. You can also show only the highest energy electrons. So if I'm not showing all the electrons that are coming out now, I'm only showing the highest energy ones, the ones that are going to make it to the end. So there you can see that now that those ones all have the same velocity. There's one stray floating around, but those ones are all only the highest velocity, not the full spectrum of velocities that you get. Because some of the electrons are being released not right at the surface but just below the surface, so they come out with a little less energy and so on, despite the fact that the incident photons have the same amount of energy in each case. So I hope that this was a relatively clear presentation, because what I've been trying to do is present the features of this app as a model of the photoelectric effect, not so much to do here's the physics of Einstein's first quantum model for the quantization of energy in photons, and here's how the photoelectric effect and the measurements we can take demonstrate that science. That's something that we'll do in the content lab, and that's also something that you're doing in your write-up, and you're thinking about how this lab works, and how, again, remember to do the teaching part. How would I actually teach this in the laboratory to my students? How would I make it transparent and clear, and would I use one session or multiple sessions, and so on? And again, also, what are the affordances of using a simulation over using the real apparatus? Because there are certain features that are much more clear and explicit. You can physically see the electrons in this simulation, for example, whereas, of course, you wouldn't be able to in a real photoelectric effect apparatus. You would only be able to see the current and kind of infer the presence of the electrons from that. So I hope that's helpful. I hope you get a good sense of this apparatus, this particular app. There are other photoelectric effect apps around the web as well. You could have a bit of a play with those and do a bit of a compare and contrast in your write-up as well. And hopefully this one simulation prac among all of the real pracs is something that gives you a sense of possibilities and how you might teach in the classroom. Thanks a lot. Bye.